Today we have a morning session only with a few, not all our speakers are arrived. Oh yeah, Anthony is here also. We are missing one. But we'll start with Rene who is a professor at Université Paris-Dauphine, and he's going to talk about demand response. So it's a nice follow-up on yesterday afternoon session. The floor is yours.
Thank you very much, Pierre. So first I will start with a random talking, so it will provide time for other people to get in the room. So I would like to thank Pierre, I would like to thank Louis and Anna for organizing this workshop and for inviting me to present this work on demand response.
The microphone is on.
Yes, you're right. Now, you hear me better?
Yeah.
Yes. So to present this work on optimal response, it's a joint work with Dylan Possama, who is a professor at Columbia University, and Nizar Touzi, who is professor at Ecole Polytechnique. So thank you a lot. First, I'm very impressed to be here in Cambridge, and it's the first time that I give a talk there under the supervision of Sir Isaac Newton. So I looked at him yesterday, and I was surprised that his portrait is not there, because if he was there, then he would have a chance to look at the talk. But in fact, he's not. He's staring at you. So look at that. So he's staring to be sure that in fact you keep attention to the speaker. So so I found that very, very funny and very impressed to be here. So okay. So I had some clear instruction. I will stop whatever it takes at 45. Okay, so we'll have 15 minutes for exchange, and I guess there's going to be some questions. So here is the agenda. The agenda is rather packed, but you're going to see that it holds. So first I'm going to motivate our model, and then I will describe our model. Then I will give the optimal contract. I will not enter into the details of how we compute the optimal contract. The paper is already available in archive. There are all the details of the computations, and it is provided in the paper. But here in the talk, I will only provide the solution, and then I will try to focus on empirical results. We calibrate our model and we try to figure out what can be the benefits of this kind of demand response with a responsiveness incentive, and then if I have time. Because there's always question about that. You're going to see mathematics everywhere, and so in the end, generally people ask about what are you going to do in real life and blah blah. Because of the pressure of public, so I have to put something like this, and then I will talk about perspectives. Okay, so you're aware that there is a story of climate change and that power systems are to be decarbonized, and so we have to get to nearly zero emission power systems, and to get to this point there are many technical solutions, and there is one technical solution that I find very interesting because it uses a lot of applied mathematics. It is demand response. It is demand response, and I'm not the only one to think that it can be useful, because everywhere in the world people are spending money to invest in demand response. For instance, in the UE, they are spending 45 billion euros to install everywhere smart meters, to reach 200 million smart meters. So it's an important investment. Per consumer is 200 euro per consumer. So maybe for us, I hope for you, not maybe for the PhD students who have lower salaries, but it's not a huge difference, but you have to figure out that 200 euros for many people, it's an important investment. So I'm going to focus on demand response, and the interesting what is demand response? Just to remember that, first it is a contract. It is a device which is purely a social device, because it is a contract, and it is a contract between a producer or retailer and a consumer. It's a contract between the two, and the contract says that the consumer is going to pay a lower fare for his electricity, a lower tariff every year or every day of the year, except on certain days. Except on certain days decided by the producer on contingency events For instance, there is a peak of consumption or any other event, and then it's going to trigger a price event, and then for the consumer, it's going to be much more expensive. Okay, and the number, generally, the number of days is written at the inception. In France, for instance, the most popular demand response contract, there are 27 or 28 days during winter. Okay, and this form is named dynamic time of use. It's going to denote the time of use. Okay, so here is an example. I'm going to use this example for calibration. So it's going to go back to this example a lot. So it's the example of low carbon London pricing trial. All the data are available. So Simon Tardemans worked on that. He's not here today, so he cannot contradict me. Okay, so I can say anything I want about it. Okay, so it's a large trial. There were more than 5,000 households enrolled, and there is a control group of more than 4,000 people. And the control group, they hold only a standard tariff, and the standard tariff is 14 pence. Okay, but there is people who are enrolled in the dynamic time of use tariff. It's around 1,000 people, and these 1,000 people, they will pay on normal days, they will pay less, 11 pence, look, 3 pence less, but on many days. And when there is high price days, like today, it's very cold, 6 times the price, look, it's more expensive. And also they tried low price days. They try to provide incentives to the consumer to consume more, okay? And I will focus only on this one. Okay. So, and there were in this trial, there were something like 70 price events. Okay, it's a lot. Okay, so some remarks. There has been a lot of demand response programs everywhere in the world, and it is known that they provide average reduction of consumption. So if people try that, because it works. Somewhere it works. People, when you send a price signal that tomorrow the price is going to be 6 times higher, then people, they do something. Okay? You don't need an economist to say that. Okay. But in fact, there is a large variance in responses. There is a lot of variance between trials and programs I'm going to provide. And also there is variance within a trial. When you make an experiment, you're going to see that there is a very large variance in their response. Okay, so here is, for instance, variance between trials. So it's taken from a paper by Farouki and Sergi in the Journal of Regulatory Economics, and they make a survey of a lot of demand response pricing trial. And what is interesting for us, it is the critical peak pricing. And all these ones, it is exactly what critical peak pricing. They send a signal exactly like so. And look at that. It can move from 10%, 10% around there, 50% more than. So there is a large variance of responses. It depends on the design of your contract, on the population, on so many factors. Okay, so but there is nothing surprising about that. You agree? Okay, but what is surprising also, there is also variance within a trial. You have a given population, you make some price events, and then sometimes people they react, sometimes they don't. Okay, so look at the low carbon London pricing trial. So I separated one part is going to be deterministic, the seasonal part, the thing that you make some demand forecast and you have a deterministic part, and I'm concentrated only on the random part for each consumer. So I've taken the 5,000 people. Okay, those are in the control group, those who are not in the dynamic time of group, and for each consumer I compute the mean and the standard deviation of the consumption reduction deviation of the X. Okay, and I compute the mean across the population, the two population, just to figure it out. So these are the mean consumption deviation of the guys who are with the standard tariff, and it is in watt. It is not in kilowatt. It is in watt. Okay? Yes, it is UK, it is London. There's small houses. It is not Austin, California, Austin, Texas. Okay, it's 13 watt. Okay, small boilers. Okay, so they are ready for climate change. So 14 watt here, the standard tariff, this is what they consume. And the dynamic time of use tariff, they consume 3. So they consume 3 because they have been sent the signal, so they reduce. Okay, they reduce. And because p-value, this number tells me that these two quantities are different. I cannot reject blah blah blah. Okay, these two guys, they are different. Okay, I just put that to show that it is science. It is not just but in fact I did this. But, okay, but you see these, they are different. But these ones, in fact, they are a little different. But p-value, you cannot distinguish them. Okay, so it's just to say and to provide motivation that okay, people they want to react, but they have their life. And when you send the price signal, they have their life. So sometimes they do the job and sometimes they don't. And in fact, there is a reduction. There is a reduction of 10 watt in average. But regarding variance, people, even in this group, they are not very responsive. Huh? They take the signal, but they make the trade-off between what's happening in their life and not, and they do and so there is still a large variance in their responses.
Okay, can I ask a question?
Yes.
When you say you take the deterministic part
yes.
out, did you make it a function of temperature or?
No. Very simple. Huh? I made like this. Just you're going to say, and why I do that? Because exactly this variable, which is going to be positive or negative. You agree with me? It can be positive or negative. Huh? It's going to be exactly the quantity that I need for my model, because I need a quantity that can be positive or negative. You're going to see that. Okay, so classical demand response contract, they fail to provide accurate responsiveness. Okay, so is it possible that people... Yes?
Could you clarify that?
No, after. Because I have to stop at 45, so you will have time for questions at 45, okay? Attends. 30 ans de plage. Okay, so in this talk, what I'm going to provide in half an hour, I'm going to provide a model to take into account consumers' responsiveness. Okay? No coefficient. Consumer responsiveness, and I want to provide incentives to increase responsiveness. So I want people to provide regular responses when I send them a price signal. And our model is going to be based on optimal contract theory. Okay? So it's a very nice theory, very, very nice theory. And in particular, because there is many ways to do optimal contract theory, we're going to do the hard way. We are going to do principal agent moral with continuous time model. So we're going to see that. But it's going to be very, very nice. And we're going to provide, in our model, this is why we can make the analysis of the model of the contract very, very precisely, because we have closed form solution for the optimal contract in the model that we're going to design. We are going to have optimal contract in the case of linear energy value. So it's a special case, but it's a very important case, and we have everything analytical, and we can provide the explicit form, and we can analyze this. And thanks to this closed form, we can make the calibration of our model, and we can provide an estimate of the potential benefit for responsiveness incentives. So in half an hour, this is what I'm going to present. Okay? Okay, so let's do this. So the model. So it's going to be a model of interaction, of commercial interaction between only one producer and one representative consumer. I suppose there is one representative consumer for all the millions of people who are enrolled. So there is only one consumer. And the consumer, I consider only the deviation from deterministic part. Okay? This is why I was interested by that. Because this quantity can be positive or negative. Okay? And the guy, when you see things in blue are controlled for the consumer. This is decision variables for the consumer. Things in red are parameters. Okay? So the guy, he has an initial deviation, and then he can make effort. Capital N is the number of usage of electricity in the house. So there are many uses, TV, oven, lighter, whatever, shower, whatever you want. Okay, I don't know if shower is electricity, but okay, bon. So many usages. And AI is the effort the consumer can make to reduce his consumption. Okay? AI is the effort he can make to reduce his consumption. so this is why there is a minus, and AI is going to be positive. Okay? If you limit the model to that, it's not necessary to have the theory that we use in this paper. But in this paper, we do this. The consumer can also reduce the noise of his response. He can reduce the noise of his response. W is a noise. It's a Brownian motion. So it's a noise. If he does not make any effort, the noise of this response on usage I is going to be sigma I. But if you make an effort, the effort Bi is going to be a number between 0 and 1. If I don't make any effort, Bi is 1. If I make effort, I reduce Bi and then the noise reduces. Okay? This is the model for responsiveness. If I make effort, I reduce the noise of my response. Okay? And what I measure, what the producer measures, is only going to measure X. I'm going to explain this. Okay, and what is the objective of the consumer? The objective of the consumer, he has a utility for, he has an energy value, F. This is this electricity consumption deviation. F transforms this quantity into euros. So F is euros. Okay, and he has a utility of his deviation of consumption. But he has a cost of effort. Okay, if I make it is costly. It is not free. It is costly. Okay, so and you want to maximize over the effort this quantity. Also, it's going to receive XI. XI is going to be a payment by the producer. People are going to be paid to do efforts. It is known that some people do efforts freely. It is known. RTE make experiment on that with Britons. Okay, Britons, they can do efforts freely. Okay, it's particular people, but it works. Okay, and the consumer is risk averse, exponential utility, risk aversion standard with the parameter R. F is concave. And here is the cost function. We designed a special and analytic form for the cost function. So it's going to be quadratic in effort for the effort on the drift, for this one. So it is strictly convex like this. And with parameter, each usage is a parameter mu I. Okay? So the more effort I do, the more it is costly. And for the effort on the volatility, beware, because the making effort is to bring Bi to 0. This is why there is a minus here. Okay, so the more I make an effort, it is strictly convex. And there is a parameter which is important, which is lambda I, which measures the cost of effort for reducing the noise. Okay, again, this one is going to be C1 and this one is going to be C2. Okay, so this is the consumer. And now the producer. So the producer is also trying to maximize his expected utility. But his expected utility, the money gets out of his pocket. This is why there is a minus. Because the money gets out, the minus. And he has a cost of producing the electricity. It's a production cost function, it is G. This is why there is a minus. And, cherry on the cake, we can also take into account a cost for the quadratic variation, which is the volatility of consumption. The more the volatility, the more it's going to be costly for the consumer. So we can, and H is going to be the direct cost of volatility. Okay. This quantity is just the volatility, it's a quadratic variation. It is the sum of the squares, okay? Okay? I don't know if you're familiar, because, so, roughly it is the sum of xti plus 1 minus xti to the square, okay? So you do that in MATLAB, it works. Okay, but it's fancy to write it like this. You look like a scientist when you do that. Okay, so, and the producer objective is to, alors, the problem objective is very difficult. I'm going to say that. The problem of the producer is to maximize over the contract. Xi is going to be the payment, so it's going to be the contract. And when he writes the contract, the consumer, what does he do? He computes its optimal response. It is a Stackelberg game. You know that. Optimal contract theory is Stackelberg game. I design the contract, the guy only makes the computation, and then he say, if you write the contract like this, I will do that. Okay? And then you need to do that. And there is also the participation constraint, which is very important. And in our case, it's going to do the nice guy hypothesis. So we are going to suppose that the reservation utility of the consumer is that I will enter into the contract if you at least provide me the utility I have without contract. Okay? Okay. So this is the model. This is entirely the model. There are 2 slides. Okay, so some remarks. Some remarks. The producer does not observe the efforts. Okay, so this is why there is unusage. It does not observe what is happening in the house. It's only measuring the total consumption deviation. It does not know what is happening in the house. Okay, in this situation. And the consumer, it's a she, the producer, because it is the smart guy. So she only observes the consumption and the quadratic variation. The quadratic variation can be measured. Okay, this can be measured. Alors, the thing is, the problem is very difficult because it is non-Markovian. It depends on the trajectory. Like, okay, there is a sum from 0, so there is a period of time. So the guy is going to observe the trajectory of consumption, and then for this trajectory it is 2 pence. For this one it is 1 pence. For this one it is minus 1 pence. This is what the producer has to write. A very, 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 very large list of for any trajectory what's going to be the payment. It's a very difficult problem. Okay, and one remark, because I have to introduce the Hamiltonian of the consumer. Even if there is no contract, the consumer can make some efforts because of risk aversion. You see, here is the problem of the consumer. Here it is. Without contract, this problem is an optimal control problem. I can make some effort. He will never make efforts on the drift. There is no reason for it, but he can make effort on the volatility. Okay, and so this is why we can introduce the consumer's Hamiltonian, who is going to denote Z, H, like this, of Z and gamma, and it's going to be exactly the Hamiltonian related to this optimal control problem. Okay? And so H, it is in euro. H is the euro. If I get, it is euro. Okay? It is the optimal quantity of money that he can make. Okay. And what is the optimal contract? What is the optimal contract? So, thanks to a paper, we know that the optimal contract is this guy. The general solution, it is this guy. There are things which are in blue, and I'm going to explain. So the optimal contract is going to be of this form. So there's going to be 3 parameters. An initial condition, which is going to be the initial payment to fulfill the constraint of participation. I'm going to explain. And then there's going to be a payment rate, capital Z. It's going to be a stochastic process. And it's going to be a payment rate for the effort that the guy does. And when you observe the variation of the state variable, the deviation, when you're going to observe the x. What does it mean? It means if you observe that dx is decreasing, then you pay z dx. And if it's increasing, you also pay z dx. But you observe this quantity and you pay the payment rate is z. Okay? For the variation of the quadratic variation, you're going to pay gamma. Okay? This term I will explain just later. And then you subtract, there is a minus here, you subtract this quantity. And what is this quantity? This quantity is exactly the utility or the money the consumer gets by his efforts. You know that. But what does the consumer ask? The consumer asks to be at his participation constraint. He does not ask to make money. So you take the money, all the money he can make by the contract, you take it out of him. First, you take it out of him. This is why there is a minus. And if you write a contract like this, the theorem says whatever the processes Z and gamma, whatever they are, you will put the consumer exactly at his reservation utility. You will put it exactly at y0. You will put it exactly, the y0 which is here, it is exactly this. Okay? So if you want to put the consumer at his reservation utility, here you put exactly the certainty equivalent of the reservation utility. And then you're going to be sure. And why is it a very, very nice result? Because when you have done this, you can use Z and gamma with the payment rates to optimize the utility function of the producer. Because whatever Z and gamma, the guy is going to receive this. Okay? So this is the reason why it works. Okay, so now the result of the optimal contract. So you make, alors, between this slide and this one, there is a year and a half. Huh? So just now, because I suppressed all the computation, but it took us a long, long time. Okay, so in the case where, now just to see that I've worked, it is not that trivial. Huh? So if you suppose that we are in the case where the energy is, the value of energy is linear, so the energy is linear, it means that for the consumer, f of x is kappa x, okay? And you denote by delta the discrepancy between f and g. So if delta is positive, it means that energy has more value for the producer than it is costly to produce, okay? Delta positive, it means energy more valuable for the consumer. Okay? Alors, I should not, bon, il ne faut pas tomber. Okay? So, C second best, it is written, it is second best. But this is why it is SB, it is second best. Well, I don't explain. So, it has exactly this form. It has this form, there is a blue part and a red part, and I explain. Z, SZ, SB, and gamma SB are the payment rates. This is what I look for. What are the payment rates? How much I should pay the consumer? One result is that those two guys are deterministic function of time. Okay? So there are some, you can compute them. Why you say, you should be surprised and why? Because normally they are feedback on the state. If it deviates a lot, hop. But in the particular case where the energy value is linear, it is deterministic function of time. Poof. And we can compute them. So it is like this. This is the certainty equivalent of the utility reservation of the consumer. This is the initial deviation. And look at that. You subtract all the gains the guy is going to make. So it is minus. And then there is a payment rate, which is this and... Alors, blue and red. Why blue and red? Because there are letters everywhere. The blue is a constant. Computed at time 0. I can compute exactly the blue term at time 0. This term is a constant. Okay? You agree with me? This is deterministic, this is deterministic, this is a deterministic function. Boom! 2 pence. This is a value. I don't know, maybe it's positive, maybe it's a value. It is euros. It does not depend on the effort of the guy. But this depends on the effort of the guy. If you observe a trajectory, negative trajectory is reducing a lot, there is a minus, you're going to give money to the guy. Okay? If X increases, you're going to take out money of the pocket of the consumer. Okay? The same for the quadratic variation. If the quadratic variation goes in the sense you want, it decreases, so there is more responsiveness. Bing, you're going to give him money, because gamma is going to be negative. And if it is the opposite, you're going to take money out of him. Okay? So the blue part, deterministic, the red part, random. And I have the dynamic of what is going to happen. Okay? So this is responsiveness incentives with now, and an important case, and what happens if I subtract, if I consider that I don't want to put responsiveness incentives. It is important because in low carbon London experiment, there were no responsiveness incentives, and I want to calibrate on that model. Okay? So the optimal contract in this case, I have. In this case, it's much more easier here because there is no double effect between volatility and drift, and things are even more analytical. So in this case, always blue part and red part, constant, depend on the effort of the guy, and I know exactly the payment rate. It's a deterministic function of time which depends on all the parameters, if delta is negative, if delta is positive, and lambda is this constant which depends on the relative risk aversion, on the volatility, and on the average cost of effort. Okay, so I know everything analytically. So I can calibrate. Okay, this is why I can calibrate. Alors, can I make some, no remarks because I'm running, so empirical results. So now empirical results. I take this guy and what to say? I say, okay, low carbon London. Okay, so I have those bunch of data. It's very, very, very useful. Very useful. Okay, And what do I say? I say that low carbon London is something like demand response pricing trial without responsiveness incentives, so it fits in this setting. Okay? It fits in this setting. Okay, so now I need to have some little imagination to calibrate the stuff. Okay, so here is the parameter shopping list that I have to find. Okay, the duration of the price events, the volatilities, the energy value, the direct cost of volatility, the risk aversion parameters of the consumers, the cost of efforts for every usage. Okay, so it's a very long list. Okay, but so first I say that the etas are going to be 1, and I will consider only one usage because in fact I don't have the information of what is happening in the house in the low carbon London. So there are other bunch of data where it is possible to have what is happening in the house. Here it is not. And for me, thanks, because now I have just one parameter mu and one parameter lambda to estimate. Okay, and there are the blue parameters and there are the red parameters. The blue are nice, but the red are not nice. No? Okay, so this one are very easy, and this one are no, not very easy. Okay, so the price event duration it's 5 hours, so because it's the data. The cost parameters delta and kappa. We know the price of the contract in the low carbon London. So people were paying 67 during peak hours, 11 off peak. So the value of delta is roughly 55. I'm going to make some variations of that. Alors, consumer risk aversion. Consumer risk aversion. In fact, it is possible to estimate this guy because in fact people to be enrolled, they received money. So the guy from EDF Energy, they called people and they say, would you like to enter into the low carbon London pricing trial? We were going to give you a little money to enter into the stuff. We're going to give you 100 pounds upfront and 50 pounds if you complete the trial. Okay, and so there is the fixed premium and there is a risk in their bill of 23 pounds. I computed, so it gives me an estimation of the risk aversion using that it is a constant absolute risk aversion utility. So 0.57 per pound. And for the producer, it is the case also. There is a large literature on that. I look at the time, don't worry. There is a large literature about risk aversion and risk premia on short-term market. You don't know if you know that. Finally, it's a very useful literature because, in fact, if you look at this literature, you will find that many papers, they find consistent estimation of a parameter P is going to be 0.6 per pound. Okay, so you look at the papers, and you will find, and you look at the papers, and so look at that. At first, I figure out that the consumer would be much less risk averse than the producers. I had the idea like this a priori, and in fact, it is not. It is not 0.6 and 0. So it's very close. Okay, in my model. Okay, for the price per unit cost of volatility H, you take your mind out for that. So I take a value of 40 euro per megawatt hour. I look at a lot of things. It's difficult to take large values for that. So I wanted to have a large value, but in the end, it is useless. What makes the thing work is the risk aversion. It's because people are risk averse that they want to have responsiveness. And we put the direct cost because we can do it. But in the end, it's not that important. Okay, and so now I have to calibrate the most difficult part, which is the behavior model of the guy. I have to compute mu and lambda. Okay, so for mu, I have something. I have to do something. So I know the relation between the reduction, the average reduction, sum from 0 to capital T of the deviation, the expectation divided by 1 capital T. This is it. And I know exactly this quantity with respect to the model parameters when I use when I use exactly this model. Puff, I know that. I know the X, puff. So I can compute. Okay? I can compute this, puff. So I know exactly this quantity. So I know that this quantity in the pricing trial, it was something like 10 watt. This quantity is 10 watt. So I resolve, poof, 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 and I know delta, I know t, I know sigma, I know everyone, so I know mu. Up, mu. So for mu, it's done. But for the lambdas, I tried. But there is no responsiveness incentive in the low carbon London pricing trial. Okay, they did not do it. So whatever I do, there is no way I can estimate this lambda. You agree? If I do yes, I estimated, you say, that's okay. Bon, there is no way I can do it. So I make a thought experiment. What would be the highest cost the consumer would bear to reduce volatility if he was to respond to an incentive? I have to make, I have to do something. So I make this, an answer I can compute using the control responsiveness model. We numerically compute a lambda. Okay. And in the paper, I check that the cost of effort for responsiveness is much lower than the cost of drift, of reducing on average the consumption. Okay? So now I have all my parameters. Okay? So I make the comparative static now. So I want to compare to my co-author. I say, yes, it's very nice mathematics. It's beautiful. Really, only an analytical solution. But can we convince someone to invest in those kind of things? Okay, is there an economical benefit for the producer? So on the left, on the right, it is uncontrolled responsiveness. It is standard demand response contract. And on the right is with responsiveness control. Okay, so reservation utility is the same. I don't decompose this. I have 5 minutes left. So the guy is going to pay, here is going to pay, it is in pence. Huh? It is not in pounds, in millions of pounds, it is in pence. Okay, so he's going to pay the guy 1 pence 22. Excusez-moi, I don't have the change. Okay, 1 pence 22, and there he's going to pay it a little more because he's asking for more efforts. So it's normal that he pays more. Okay? Alors, look, but I don't care about that. Okay, you pay the guy more, but do you make more money? Okay, so without contract, the cost is negative. The producer is bearing a cost. It is negative. His objective function is negative. It is all the certainty equivalent. It is negative. It is 0. I compare carrots with carrots. Okay, so it is negative. The two guys are negative. But with contract, ding, and contrast, he moves from here to here 0.33 pence. But here, paf, 1 pence, much more money. Okay, the average reduction, the guy here, it is the 10 watt that we have seen, is going to reduce a little more, and look at the volatility. The volatility on the period, it is 200 watt, and there it is 160 watt. So this is, I have 5 minutes left, this is the nominal situation. So what happens if I move a little the parameters, and in particular, there are 2 parameters, there are many of them, but in fact, there is the duration of the price event, and there is the delta, the discrepancy of energy value between the producer and the consumer. If there is no discrepancy between value of, if delta is equal to 0, we're not going to make so many exchange. Okay, so nice picture. Okay, look at that, nice picture. And then I'm done. Okay, so this is it is the value. So the more you go from here, the more the energy is costly for the producer compared to the consumer. Okay, so the more it is costly, I want the guy to reduce because it's very costly for me to produce this energy. And here it is the duration of the event: 2 hours and 12 hours. In low carbon London, there was 1 trial of 24 hours. Poor guys. Okay, in plain winter. Okay, they want to see people who complain. Okay, so look. There is a 0 line. It means below this, in this, there is no gain. If the duration is too short and the discrepancy of energy is too small, you don't care about responsiveness. You don't. Okay. When are you going to care? We are going to care, for instance, even for low discrepancy value, but long duration. Because then you have the time to observe what is happening by the consumer. You know if it's random who is really making effort. Okay, And so look, 26% gain, 54%, and then more than 100%. Okay, so I skip the volatility. The morality of this story, very important. And then I'm done. I promise, look, 2 minutes. 2 minutes for the morality of this story. Very moral. Okay, so you remember there was the contract, there was the blue part, and there was the red part. Okay? The blue part is a fixed constant. So one colleague of mine said, yes, it's very interesting, all those computations to tell me that the optimal contract is a fixed part plus a proportional part to the effort. Okay, in the commercial business they know that. Okay, so here what I plotted is with responsiveness control the total payment depending on the duration of the effort. Okay, so here you have the duration of the effort. In blue it is how much you have to pay the consumer on average. It is the certainty equivalent always. The total payment, so the blue part plus the red part, and in red here it is without responsiveness control. So no surprise, you pay the guy more. You ask for him more effort, so you pay the guy more. Okay, you don't need a PhD to see that. But then you separate the two parts, the fixed part and the random part. Okay, what do you see? You see that for the without responsiveness control, you're always going to pay the guy a positive payment. The fixed part is always going to be positive. And look for with the responsiveness control, for a long effort, it is negative. So first you take out of the money of the guy 8 pence. I take 8 pence out of your pocket, and then look, if you have some success, then I'm going to give you a lot of money, 15 pence. Okay, so this is the moral of the story. This is a moral story. If you want to induce efforts on a regular basis for agents, okay, so what do you have to do? First, you decrease their income compared to his peers. You decrease the income compared to his peers. This is why commercial people, the guy who are commercial, they have a fixed salary which is very small. But then, when they sell the Airbus, bingo! Lot of money, champagne, okay? So this is a moral story. Look, for CEOs of listed companies, we're going to make another paper on that. Okay, so I am done. It is 45, so I am done. I'm going to, maybe there's going to be a question about that and question about perspective, but I'm done, and thank you very much for your attention. Okay.
Are there some comments or questions, clarification questions?
Alors, Sean. No, the answer is no.
I won't make any comments on the morality of the speaker or the content. But the reality that seems missing is that, in most applications, you want to give them warning, and there's like in 2 hours there's going to be an event, and you let them know, and then they preheat their house at 1 degree and their water heat is 1 degree, and their disutility is 0. And so A, could you possibly incorporate in your model, and B, why do results seem to reflect that reality anyway? Seems like 0 disutility for a price event of 2 hours, which is consistent with time constants.
Very interesting. Alors, the first question, can I put in my model the fact that
the warning? The grid operator knows
anticipation.
They know they have so much information that the user doesn't have, and if they share that information with the consumers, they could prepare for events. That mismatched information is one of the big problems, I think.
I don't know for this. I have to figure out. I don't understand precisely what kind of information the producer should send to the consumer.
In New York, every 2 p.m. there's a price. There's a spike in power.
Okay.
And you could flat that out easily.
Okay.
With the right control.
Okay.
And with prices, maybe I don't know. But,
I don't know if it's possible to do that. Alors, regarding the second one, there is a reason. I answer to the second part because in fact you need time to. This is why you are not going to pay the guy, or there's not going to be any efficiency for short-term price event. It is because you need time to separate the realization of randomness and the realization of efforts. This is because of the Brownian motion and the stuff. The problem of principal agent theory this guy is, okay, so here is the guy. So when you observe, you only observe X, and the guy is making some effort, but there is a Brownian motion. And so if the period of time is too short, you don't know if what you observe is the result only on the noise, or really there is an effort. If you observe a small trajectory descending, is it because he was lucky, or is it because really he made some effort? So for short term, for short period, for short capital T, you don't know the thing, so it's very inefficient. So I need time. I need time for that. But for the first one, I don't know. We should check. Mr. And then you. Yes, yeah, he raised his hand.
Are you? Sorry.
Yeah, he was not crashing his. No. Okay.
Should BI be taken independently of AI? Because I'm seeing here that they are actually independent. Can you also have AI, BI as a functional of AI?
Alors, no. They are independent. Yes. This is the. Yes. It's a behavioral model which is very particular. You agree with me? This is your question. Because the guy is making some effort on the drift of usage and an independent effort on the responsiveness. Okay. But you can explain this like this if you repeat, because we have ideas of how to implement this concretely. Okay. So you could say that, in fact, you repeat the experience. And sigma, this guy, is independent in say, do I constantly make effort, for instance, to switch off TV when there is a price signal? Okay? So I will reduce, but each time I will reduce by, I don't know, je sais pas combien, but will this effort AI will be constant? And this is the BI. This is why it is independent. This is why I can consider that it is independent. Okay? I make a reduction, I switch off TV, but do we do it regularly? Each time I send you a price signal, do you do it regularly? Okay? First him, because he raised his hand first.
I mean, it goes along what you were saying.
Right.
Here it's memoryless. We generalize AI and BI in terms of policies, and you have kind of a lag. So what's the last time I reacted for you, or I did something for you? And then maybe your ability to respond or willingness to act is a function of how long it's been since last time you acted.
Yes. My model is memoryless. And there is a paper by Josco who is saying that about demand response, about the fatigue.
Yeah, exactly.
The fatigue. And in my model there is no fatigue. You can trigger an event 10 times. The guy has no memory about the effort he made.
Yeah.
So yes, but then this is difficult because you need to have another variable, a state variable, to say how many price event did you trigger, and does the guy is.
But that could then end up in your Y0. Like if you say it's a number of shots, and say we've agreed on fatigue, it's this number of shots, and we're not discussing fatigue anymore because you get the argument for this number of shots.
Yes, it could be in the initial deviation.
Yeah.
But it could be in the initial deviation, and the more you trigger, the more x0 has moved.
Yeah.
Yes, it could be. But it's true that in this model, I don't have the fatigue and those.
Yeah, thank you. I was a little bit confused by the answer for the behavioral model, because I think the more you try to, let's say, make the response regular, so you reduce the noise, at some point it stops being an effort, right? It's your new normal behavior.
Huh?
It stops being an effort after some time. If you constantly, let's say, respond in the same way, so you stop, let's say, you reduce the effort. It stops being an effort. It's the new normal load pattern somehow.
Okay.
How do you take that into account?
No. It is the same. There is no learning of the consumer. this model of consumer, which is very, very simple and very out of the, like this, huh? We pick that, okay, we did not make any behavioral studies, huh? Okay, about that. There is no memory, there is no fatigue, there is no learning. So exactly what you say, if the consumer moves his habits to a different kind of consumption, I have to recalibrate these things. This model is no longer valid. Okay. Okay, so maybe for that, because I had some perspective, and we will answer, because you say, we are not going to stop there. Attendez, just, we only considered one consumer. So first we need to do what's going to happen if there is a bunch of consumer in interaction. So those things. There is adverse selection. We don't know the parameters of stuff. You told about memory. We need to take into account the fact that people are going to get bored about these price events, and we cannot repeat them. There is also one thing, which is, here I calibrated the model like this because there was low carbon London. But in real life, we want to make some real life experiment. We are in discussion with EDF to do something in the line of low carbon London. But then, what parameter should I take for my contract? It's going to be very difficult. So there is something like learning. I need to learn the behavior of my consumer to design something which is going to be efficient. So there is a lot to do. Yes.
Can you say a little bit more about this, the way the consumer sees this contract, particularly the payment, the minus H component?
Yes.
So I'm going to do some work for you.
Yes. Look.
And you are going to calculate how much it's cost me to do that work, and then take that away from.
Yes.
Get back to its morality.
Yes. But I have an answer for that. Thank you. In an optimal contract theory, it is because in optimal contract theory, the thing is, it's the model for the agents are very simple. They are expected maximizer of utility and blah. And to avoid that, you turn them into slaves. There is this participation constraint. If there is no participation constraint, people are slaves. Okay. Okay. So here we are. So the contract is like this. Why is that? Because the guy only asks for Y0. You agree with me? He asks for, I will enter into the contract if you give me 2 pence. Okay, but I am going to, this guy, Z and gamma are going to trigger efforts. You're going to make some efforts. So you have your function GA is going to take a certain value. Okay, but maybe this value is above 2 pence. But you ask only for 2 pence. So why would I give you 10? This is why. Why do professors of universities are less paid than engineers? Why? Because you do things without incentives. Okay, this is why we get less paid from engineers. We have to we have to pitch them and to strike them to work. This is why we are less paid, because we do things without effort. We are being subtracted the value of the efforts. Okay, this is why you have to subtract this quantity.
I can see that. I'm wondering how it works. So, from the point of view of a consumer, what does this actually look like? What does it look like?
Alors, no. That's an important question, because when I entered into this theory, I was like you. It's how it's going to work and why it's going to work. Alors, it works. First, it works. Okay, and how it works when you look at this quantity. When you say, okay, this is the optimal contract. It's when I say to Madame. Because my co-author are convinced that we're going to write that in the contract with millions of customers. Okay, so I try to explain them. No, it won't work. It will not work like this. We have to adapt things. But basically, if you believe, there is the fixed part, you're going to give people, and this is exactly what you do when you say to people, your fare of electricity is going to be 11 pence instead of 14. This is exactly the fixed premium. But then, when you're going to be a price event, the quantity which is here look like the 67 pence. If you don't deviate, then you're going to pay a lot more. But if you deviate, then you're going to make money. So we recover exactly, we'd say that exactly, we recover the logic of optimal contract demand, of demand response. It is the same logic. I give you a little money, but the way it is expressed is very different. It is not a discrepancy of price of electricity between 14 pence and 11 pence. It is different, the way it is expressed. I give you a premium at time 0, and then I observe what you do, and if you make some effort, then you make money, but if you don't, then you will pay your electricity 67 pence forever.
You're talking here about motivation.
Yes.
And I strongly suspect, because a lot of these trials have shown that after several months people's behavior changes.
This is
they actually perceive they're playing a game. The example being the university professor. You enjoy being a university professor, therefore you need to be paid less.
So this is why you complain, yes.
So instead of it being fatigue, it's actually a Hawthorne effect. So people are, the score, the money, is part of the score in a game. It's not a financial incentive. When they become bored with the game, then they play it less. Well, I agree with someone who said the behavior may have become just standardized.
Yes.
So if the cost of making the change is very small to them, then they may just do it. So when you construct your trial, can you design it in such a way that you detect whether they're playing a game or whether they're getting an economic incentive?
Fine. If I can do that, I will be very happy. But the problem is the following: when you design a price trial, even the low carbon, you have to write at time 0 the contract. You have to write it in a definitive way.
I suggest perhaps that they have an option to leave the contract.
Okay.
Which will show they've lost interest in the game.
Oh.
The option, and you design it right, you can detect that they're no longer interested in playing the game.
Maybe, but I don't know if it is optimal.
Optimal in which? Well, it's often harder in the real world to be sure whether things are optimal.
I don't know.
All right, very last question.
Yes, it's just follow up on it. I think it's very easy to detect that they lost interest when they stop responding, right? You don't have to leave the contract for that.
Yes, but we have to do it a little, because maybe at some time when you repeat the experience, in the low carbon London there are many detailed analysis of the responsiveness and why people respond or not. Because sometimes, in fact, there are some period of time where people, they lost, we don't know if they lost interest. They have some particular constraints on this period. But if you repeat it enough, then you can observe if they have lost or not. But we need a little time for that. Okay? So, I think we are done.
We need to close. So thank you very much.
Okay.